Go.
Hello.
Hello, Mr. Ryan. How are you today?
Hello.
So we have talked about the subarray. Yeah, remember? I think in the
Subway.
first subarray.
Subarray.
What's subarray?
It's a thing. It's array. That it's a type of array.
Subarray. Yeah.
It's a type of an array.
Continuous. It's continuous. Okay.
Yeah.
Remember, we have a few concepts. Subsequence. Yeah. Subsequence. Yeah, and subarray. Yeah, or substring. If it's a string, it's substring. Subsequence. Subsequence is that you can remove one or more elements from the original array or string, and it becomes a subsequent. It does not have to be continuous. Subarray is continuous, right? Alright.
Yeah.
We have to be continuous. Okay. We have talked about. I think we have talked about this. The max subarray, right? We want to calculate the max subarray sum, right? So what's the max subarray sum? What's the subarray that has the most sum in this array? Alright. Have a look. You know the continuous. Continuous.
How much?
You can pick this. Yeah. You can pick this. That's 6. Yeah. Alright. Or you can pick here is 12. So the most subarray is 12, right? Yeah. Alright. Or maybe 6 minus 5.
What's the length?
Sorry,
What's the length for the subway?
What do you mean then? The subarray doesn't. Yeah. Look, 3 to 1 is a subarray. 2 1 is a subarray. 1 is a subarray. It has to be continuous, like subsequence. Okay. Got it? Yeah.
Then why can't you just do all of them?
Oh, well done. Okay, let's see. Okay, because I'm not sure. I'm just checking.
It is
It's
because like 6 minus 5 is 1 and 10 2.
Yeah, you're right. Yeah, you can put all of it. Yeah. Okay, so how are we solving this? Remember we have talked about this before.
Greedy and then.
Yeah, greedy. Yeah, and then the first approach is what? If we're not sure, we can always do this brute force. And how do we brute force? We can brute force the subarray or subarray or substring. Yeah, in what's the time complexity? If we determine the left part, the starting part of the subarray, and then we can brute force the next. Yeah. Okay. Let's try this. Okay. This is just a little review, and I'm going to introduce a new concept. Okay, a new algorithm. Okay. So let's see. Define max subarray. Right. Subarray. Array sum. And we have the numbers. Yeah. Numbers. So first of all, we want to get n. N equals length num, right? This is the length. And the max sum, okay? So the max sum is what? Let's assume this numbers is not empty, okay? It's not empty. So assert, yeah? Assert. Remember assert? N is bigger than 0, okay? Assert n is bigger than 0. And at the beginning, we want to assign the max sum to the negative. So what's the minimum? What's the smallest number you can think of?
Minus infinity.
Well done. Mass, not infinity. Yeah, infinity. Infinity is not actually not a concrete number. It's so small that you can't measure it. Okay. And then now we go to.
A millimeter.
Yeah, we for left in range. Range. We start with 0 to n, right? And then we brute force the right. Yeah, if we already decide the left part, then we go to the right part. For r in range what? We start with what? L plus 1, right? Can we start with the L? Yes, we can put up because the subarray can be a single number. So we start with the L and up to n, right? And now what? And now we want to calculate the sum, right? We want to calculate the sum. Yeah, we want to calculate the sum. Then now this sum equals what? We can do this sum what? Nums L to r plus 1, right? Then we calculate sum. And then we want to keep the maximum. So maximum answer equals max answer S, right? And then return what? Return answer. Very obvious. What's the time complexity? It's very tricky, okay? Look, what's the time complexity?
OLR. O n cubic.
Yeah, because this one, yeah? But we can improve to O(n) square, right? This is O(n) cubic, right? We can improve to O(n) square. How do we improve to O(n) square? So every time we start with the L, we put S equals 0 here. And then we just here, S plus equals nums R, right? Because every time we start with L, the sum is 0. Right? And then we start adding the subarray sum, and then we do this. Then in this case, the term complexity is over. If we do this optimization, the sum is gone. So we accumulate the sum along the way. So what's the term complexity? And what? Come on. Why you said O(n)(3) in the first place? O(n) cubic. And now I improve it. So what's the term complexity?
O(n) square.
O(n) square. We're done. Okay. So this is not new. Okay. We have talked about this before, right? This is just the review. Okay. And we talk about the dynamic programming. Actually, because at the time we didn't know that dynamic programming is also a fancy name called Kadane algorithm. Kadane. Okay, Kadane algorithm. So it's actually an iterative dynamic programming. So what does it mean? So let's use this. Let's use DP. Yeah, dynamic programming. That means that that's the maximum subarray sum that ends at index I. Okay. Yeah. Max sum subarray ends at index I. Okay, that's what you mean, DPI. Okay. So what does it equal? Is it equals that max what? Max of what? dp, the first previous one, I minus 1, yeah? Let's do this a little bit closer. And then 0 plus the numbers I. Eric, can you understand this? What does it mean? So look, I have a few numbers, yeah? 4 minus 10, 1, okay. So at this point, the max subarray sum ending at this index is equals to the maximum of the previous sum plus this number, yeah, plus this number. Or if I don't pick the previous one, if I pick only the current number, right? Right? Does it make sense? So at this point, I can make a choice. I can choose to keep the previous subarray sum, right? Or I can abandon the previous subarray sum. So this is abandon. When we abandon it, then we start a new subarray sum is just this number. Or we keep the previous subarray sum. In this case, we add the current subarray sum is previous one plus the number of this one, right? So this is called Kadane algorithm. It's also iterative dynamic programming. Okay, iterative by dynamic programming. So we can implement it without keeping this DPI because we always look, because this DPI is an array, right? But we can implement this just using the two variables, because for every time I calculate DPI, all I need is DPI minus 1, right? Huh? Okay, let's do this. This is called Kadane algorithm. It's quite similar to the dynamic programming we have implemented in the first few lessons, right? In a long time ago. Just a little review. Just make sure you don't forget, okay? And then today we give you the fancy name called Kadane. Okay, Kadane algorithm is the iterative dynamic programming language programming algorithm to compute the maximum sum of subarray in a one-dimensional array. Okay. Usually, if we use the brute force, then that time complexity will be O(n) square. Okay, O(n) square for the improved brute force. Defined max subarray. Nums. Okay, so now how can we do this? N equals length nums. Okay, this is the same, and then we assert n is bigger than 0. Okay, we don't want to compute the subarray. It doesn't make any sense if we want to compute the subarray of the empty array. Okay. Now I have this answer. Let's say is max max to infinity, right? Right? And then I have the current sum. Okay, let's put this as 0. And then we loop over the numbers. I in nums. Okay, now what? S will be equals to maximum of what? S and what? Actually, it's maximum of I. We choose the current number or we choose the S plus I. Right? And then answer will be equals max answer of and then the current so far. Okay, S will be actually let's rename the S to the maximum ending the current index. So let's say DPI. Okay, let's put it DPI. This is a variable. Okay, DPI equals 0, and DPI equals max I. This is the current. Remember, we're talking about the current number, ending the current number. We can start with the current number, or we keep the previous sum, so which is DPI plus I, right? And the max answer equal max answer. We want to keep this is the global maximum. Okay, global maximum. We can do this DPI, right? DPI, and return what? Answer. What's the time complexity? If you look at this, what's the time complexity? Can you tell me? ON, yeah? Is ON, yes. Yes, it's ON. Okay, so let's go through this a little bit, okay? Answer, global maximum. At the beginning is is the smallest number we can represent in Python. It's negative infinity. DPI is the what? Is the maximum sum of the subarray that ends the index I as a current position. And we go through these numbers and we update it. So this is Kadane diagram, yeah. It's also DP, yeah, DP. So it means that we can choose to ignore. Look, Eric, 3 to minus 10. Okay, here. All right, look. What's the subarray of ending at minus 10? What's the subarray of ending minus 10? If I have, what's the maximum sum of subarray that has to end at minus 10?
Minus 10.
Is it minus 10? Can I include the before? Then it will be smaller, right?
You'll be infinity.
No. You'll be 5 minus 10. You'll be minus 5. Minus 5 is bigger than minus 10. That's what I mean. Yeah. But if this is minus 3, minus 2, minus 10, what's the maximum sum that ends that subarray sum that ends that minus 10? That's minus 10, right?
Yeah.
You see the difference, yeah? So DPI is the maximum. Okay, let's repeat it. Max subarray sum that ends at I, index I, DPI. So ends at the index I. Okay, so and at this point, so I need to compare what? I can compare if I keep the previous sum, right? Alright? Keep the previous sum is which is DPI minus 1 here, right? Here. This is dynamic property. If I choose to keep the previous sum, so there are two possibilities. One is to keep it, then the sum will be previous DPI minus 1 plus the numbers. Or if I choose to abandon the previous sum, then the sum will be what? If I choose to ignore any one, then what's the sum of the one ended at index I? Come on, it will be easy.
Minus
10. It will be least number, right? So that's what I mean. DPI equals max I. Max I is this number. DPI plus I is previous one plus this number. And we want to choose the maximum. And answer will be the global answer, right? Because we want to find out the maximum subarray sum, and then the subarray sum can end in any index, right? That's all. That's why we keep updating this global answer. So the time complexity is O(n). What's the space complexity? Are we using any space? No. What's the space complexity? Oh, what? Are we using any additional linear space?
1.
Oh, 1, well done. Okay, so this is called Kadane diagram, okay? Previously we have talked about it, but we didn't know it was called Kadane. We just named it as dynamic programming, but it's basically the same thing. So today is basically just the review, okay? Just a review of the previous lessons, okay? Any questions? Any questions? No? Okay, so tomorrow we're going to use this Kadane diagram to do something more, because, because this is very useful. It can be used to solve many similar problems like what? Okay, so I give you a little problem to think about, and then we can talk about it tomorrow. Okay, so look, you know the price, the stock price, yeah? Alright. So I have a price, yeah? 3, 4, 2, 1, 10. This is the price of every day, and you can only buy and sell once. And what's the maximum profit you can get? For example, you can buy at 3 and sell at 10. The profit you get is what? 10 minus 3 is 7. Or you can buy at 1 and sell at 10, right? The price, like a price, you got a price, yeah? You got a toy. Today is worth than $1. Tomorrow is $10. If you buy it today and if you sell it tomorrow, how much benefit, how much profit you can make? How much profit you can make? If today you buy, let's say you buy a chocolate, £1 today, but you can sell it £10 tomorrow. How much profit you can make? Come on, easy.
10.
Tomorrow you sell it at 10. Today you buy it at 1. What's the profit you can make?
11.
Huh?
9.
9, yeah, well done. Look, because you pay 1 today, right? You pay 1 to get it, and tomorrow you sell it at 10. That's 9, right? So we want to find the minimum. Minimum you can buy, which is 1, and the maximum you can sell is 10. Okay, but we can talk about this tomorrow, and we can use this Kadane diagram. Okay, so that's it for today. Good job. Bye bye. Bye bye.